Hey guys. All right, so hey everyone, welcome to the weekly space hangout. My name is Fraser Cain. I'm the publisher of Universe Today, and this week we've got Dr. Brian Koberlein.
Hi.
Dr. Koberlein. We've got man on the move, Dave Dickinson.
Hey, live from OKC.
Clearly some hotel that
Yet another hotel, yeah.
Chatting for a while. The internet is holding. It's holding. So we'll see what happens. We got Morgan Rehnberg. Hey, Morgan.
Hey, Fraser.
You're back home.
Sadly.
Really? You want to just stay at various astronomical conferences all the time?
Wouldn't be the worst life in the world.
And we got Dr. Ramin Skibba. Hey, Dr. Skibba.
Hey, Fraser.
All right. So we've got, it's going to be a weird show this week, I think. We've got a ton of stories that are like just interesting things that have turned up. We don't have any horrible bad news about losses of spacecraft and tragedies, and at the same time we also don't have the big, very much news from Rosetta. So we've got sort of all of the other stuff that we haven't had a chance to talk about for weeks and weeks, and there's a lot of really interesting stories here. And they're going to come at you fast and furious. Now, before we get cracking on that, we're going to just want to remind you that you can interact with us using the Q&A app. Available. So if you just click on the video, it says Fraser is interacting with the audience, and then it'll take you to another version of the video, but then there's some questions on the side, and you can go ahead and post your questions. So let's get cracking. Oh, it's like Christmas. Where do I want to start? You know what? I'm going to start with Dave Dickinson only because I fear for his internet. So, Dave, now you published something which, I mean, you got very early, I think, on getting on top of the story. I don't think a lot of other people are really covering it as early as you are. We were like 1,000 days to a monumentous event.
Till the total solar eclipse crossing the lower 48, or the contiguous lower 48 states on August 21st, 2017, this coming Monday. Michael Zeiler over at Eclipse Maps, I was just visiting him in Santa Fe, and we were hatching our plans of world domination. He runs a website called The Great American Eclipse, and he pointed that out to me, and I was like, oh, I didn't know that we were coming under 1,000. I knew we were under 3 years out now. There's only 3 more total solar eclipses going to occur worldwide until this one. And if you're like me and you've never seen a total solar eclipse, this might be the first time to actually journey to the path and get to see a total solar eclipse. Now, a lot of people live near the path, and I've heard the discussion that, oh, I'm at 95%, like the partial eclipse we had last month, where it was like 33%, 20%, and every eclipse chaser I've known will tell you that a partial eclipse and total solar eclipse are not the same. So if you're near the path, you need to get into the path of totality. And actually, I've seen an annular eclipse from Lake Erie in 1994. That's the best I've done. And I can tell you that a 99% partial, like an annular eclipse, is still pretty bright, actually. You'd be surprised how bright 1% of the sun is. It's still like a bright, cloudy day like we have outside here in Oklahoma City right now. And some towns along my trip are actually preparing. We've talked to Hopkinsville, Kentucky. They are right near one of the maximum points of the eclipse, where the eclipse is going to be 2 minutes and 42 seconds in duration. They're already preparing. Carbondale, Illinois is already preparing. Some towns in Kansas and Nebraska, they're already preparing for, see, this eclipse happens in August, so you've got, school is still out, at least some schools are still out or just going in at that time. Everybody's out. It's good camping weather for North America. People got their RVs. So I think you're going to get a lot of eclipse-curious people journeying to this one, not just the hardcore. There's the hardcore eclipse chasers that go to Antarctica and Outer Mongolia, and they go to every eclipse. I think in this eclipse, you're going to get a lot of eclipse-curious people because they live within a few million miles, or not, a few million people live within a few hundred miles of the eclipse.
Yeah. So I guess who here has ever seen a total solar eclipse?
Nope, seen an annular.
Nobody. No. So this is it, and I hope I assume most of the people watching this show have never seen a total solar eclipse, and this is it. This is the. I mean, if you live in North America, this is the one. There won't be anything like this for decades. I'm absolutely going to make a huge road trip on this one.
If you look at the climate prospects for North America around that time in mid-August, probably the better prospects are going to be toward the northwest, because this happens mid-afternoon for a lot of people, and toward the east coast in August you generally get thunderstorms cropping up around that time. So there's no guarantee. We don't know what the weather's going to be exactly like on eclipse day. Mobility a lot of times is key. From a lot of veteran eclipse chasers I've talked to, they said they have a rental car, they have access to the highway, and they're ready at the last moment if they have to drive a few hundred miles to catch the eclipse, because the weather has shifted there. They have that mobility ready to go. So.
Yeah, and so where is the sort of the beam of this totality going to start, and where is it going to end? If we sort of drew a line across the United States.
If you drew a line from the Pacific coast of Central Oregon down to the central coast of South Carolina, is where it's going to leave over the Atlantic Ocean. It's going to literally crisscross the United States. So it's going to cross over. Nashville is a big city. Columbia, South Carolina is a big city. It just misses Cheyenne. We were there a few months ago in Wyoming. It's going to be just north of Cheyenne. And if you're around the town of Carbondale, Illinois, and you hang out for another 7 years, in 2024 you're going to see another total solar eclipse crossing the other way from southwestern U.S. up to my old hometown of Presque Isle, Maine. So after
Rochester.
This eclipse drought is about to end. We haven't had an eclipse on the southern lower 48 since 1979, and we haven't had one like this cross the United States all the way across since 1919. So the drought is about to end finally.
Yeah, I remember the 79 one actually.
I don't know if anybody remembers the 1919 one.
I don't recall that one. No. Okay, great. Well, so let's give people that date so they can start making their plans. So.
August 21st, 2017.
That's it. And so if you haven't got plans to go on a road trip and appreciate this eclipse, I don't know what to say. Do I have? I will nag you, and David and the rest of us will nag you literally for the next 1,000 days. That's what you have in front of you.
I know we'll be writing about it on Universe Today.
Oh yeah. Like I said, anticipate 1,000 days of nagging. So it starts now. I think it's a great time to start, 1,000 days out. You know what I think would be cool? And I wish someone could just do this, would be to like have a symphony, have someone come up with a musical score to the eclipse, and then have a symphony play it live while you're watching the eclipse. Wouldn't that be cool?
I'll run that by Michael Zauer to see what he says.
Okay, yeah.
I think there's a classical piece of music. It's called Soul or something. I forget what the title is, but that
someone's
could be
already come
music.
up with this. Okay,
yeah.
Well, yeah, we need we need some philharmonic orchestra to play this.
There is a symphony entitled Transit of Venus that was written for the 1887
Just
transit.
went on for 8 hours. Right. Okay, great. Well, let's move on. But boy, again, you've been warned. The nagging begins. All right, let's move on. Okay, so let's talk about. I'm going to talk about this story that came up, which I think is in Brian's wheelhouse, which is using GPS to detect dark matter. Finally, a use for GPS.
Yeah, this is kind of an interesting story. For those of you who aren't familiar, the GPS, or Global Positioning System, is an array of satellites that orbit the Earth, and we use it to find locations on the planet. And basically the way this works is the satellites send off signals in which they broadcast what their position and time is. And if you have a GPS detector, it can pick up multiple signals from these GPS and then calculate where you are relative to those signals. Now, in order for this to work, the clocks have to be extraordinarily precise. So they have to be on the order of, I think, about 30 nanoseconds or so in order to work. Because if the timing is off, then your position is off by miles. What's interesting about this is that the effects of special and general relativity are enough that they affect the timings by the order of microseconds, so 1,000 times larger than the precision you need. So in order to properly do the clocks, you have to adjust the times for time dilation. You have to take a time dilation into account because they have to be that sensitive. And the fact that the satellites are above the Earth in less gravity means that they have a different time, and the fact that they're moving means that they're time dilated. So this new paper proposed the idea that given the precision of the clocks, and given that they already are sensitive enough to detect the effects of gravitational curvature, if you had a type of dark matter that's called topological dark matter or top-down dark matter, you might be able to detect one of these clumps passing near the Earth. So the basic idea is that, I guess to step back, in regular dark matter, the idea is that there's some kind of particles, and they would be pretty evenly smeared out, and so this wouldn't detect that type of dark matter. So WIMPs and axions and things like that, that's not what it's detecting. But another model, which isn't as popular, but is still there, is topological dark matter. The idea is that within space and time, you have these kind of topological defects, and they could radiate particles, including dark matter. And if that's the case, if one of these kind of defects went near an area, it would still have dark matter around it. You would still have this kind of gravitational perturbation. So the idea is, if you look at the GPS satellites, and if you've got the Earth here and some clump of dark matter passes nearby, then you would see the timing go off in the satellites. So you would detect this kind of shift in timing, and from that you would be able to detect dark matter.
And does that happen because of the increase in mass, or the change in the mass distribution? Is that why it does it?
Sorry.
I guess it's because of the mass distribution that it affects the time calculation?
Yes, because in the TD model, the dark matter can be more clumped near the defect, and so you can get a kind of a small density of dark matter. The idea with top down is it can be clumped in areas, but overall it'll average out. So it can still account for the large scale structure, but on the planetary scale, on the solar system scale, you could have small clumps.
Now, could you go back in all of the GPS data and be able to just historically look through it and decide whether or not it's true?
You could, and in fact, the authors are now doing that.
That could be a job for citizen scientists. That could be a job for citizen scientists, because you might have a lot of data to go over.
Yeah.
So they are in fact data mining now.
Yeah, and who knows? You could find all kinds of stuff. I'm sure there's such accurate time, so many signals sent by these satellites, so many times they're received. Who knows what kinds of stuff could be detected in those signals?
Every phone is GPS enabled now too, so there's more data.
Yeah. Yeah, maybe gravitational waves? Could you detect gravitational waves from GPS satellites?
I think the thing is they're not sensitive enough.
Yeah.
Yeah.
In this paper, the sensitivity is just kind of on the edge. Based upon they're just there. But gravitational waves for the type of things that we would expect would be far too small.
Yeah, amazing. Cool, okay. Well, let's move on. So, Morgan, we've got evidence that a meteorite experienced the magnetic fields of the early solar system.
That's right. One of the big mysteries that we have today in planetary science is what was the solar system like, basically, right as it was forming. And we want to know things like how bright was the sun? How much gas was there compared to hard stuff? What was the distribution of this matter throughout the solar system? And another question that we want to answer is what was the magnetic environment like early on? We know the sun has a magnetic field today. We know many of the planets, the Earth, Jupiter, Saturn, Uranus, Neptune, have magnetic fields today. But what was the magnetic environment like 4.5 billion years ago when all this stuff was just starting to come together? And of course, we can't go back and look 4.5 billion years in the past, but what we can do is look for relics of that time. And meteorites are one of the only relics of that time that we have accessible to us today. They're kind of like miniature time capsules of what the galaxy was like when the solar system, the sun, our planets were forming. And so this was a particular meteorite that fell to Earth in the 1940s after spending 4.5 billion years in space. And it's a unique kind of meteorite because we call it primitive. And this means that it's barely been changed over the course of that 4.5 billion years. Most meteorites have been knocked off of asteroids or were heated up at some point in their life or collided with something else. They've been changed over the last 4.5 billion years. That's not surprising. But there are a few out there that we call primitive meteorites that seem to us to be basically exactly as they were 4.5 billion years ago. And we can crack those guys open and we can look inside basically to see the ingredients of the solar system as seen all this time later. And one of the interesting things we find inside them are these almost perfect little spheres called chondrules. And chondrules are interpreted as bits of molten metal and rock that hit space and basically flash froze in this ultra-cold space environment. And so they preserve almost exactly the composition of whatever was going on around that time, 4.5 billion years ago. And some of them are made of rock, some of them have metals in them, and in this case it's the metal that we're interested in. Because if there's a magnetic field in this area of space when this thing flash freezes, all those bits of metal are going to align along the magnetic field, just like filings would if you put them next to a normal bar magnet. And when they freeze all in the same orientation. If there wasn't a magnetic field, that wouldn't happen. You'd see these little, basically iron filings freeze in all different directions. And how much they're lined up, then, we can relate to how strong the magnetic field is. You can imagine if the field is very strong, they're all going to be really rigidly lined up. If the field is weak, some will be lined up. There'll be a tendency to all be in one direction, but they won't be all parallel. And so by cracking open one of these chondrules, inside of one of these primitive meteorites, scientists were able to figure out that the magnetic field in the area of space that this chondrule formed was about as strong as Earth's magnetic field is today. And that might not seem surprising. Hey, we found this thing on Earth. But this was before the planets had formed. So the planets didn't have magnetic fields basically going out into space. This would have been the magnetic field that permeated the disk that the planets formed out of. And today, if you look between the planets, say between Earth and Mars or between Mars and Jupiter, we find a magnetic field that's about 100,000 times smaller than this. And this tells us that magnetic forces were very important early on in the solar system for forming planets, forming asteroids, things like that.
It's similar to the way that that geologists have been able to track the magnetic field reversals here on Earth, right? As they look at the metallic substances coming out of lava flows, and they're able to see the way the lava aligned to the magnetic field, and they could see that these actually, flip over every 200,000 years or so, and that we're overdue for one right now. But Right. So what does this sort of tell us about the conditions that must have been here in the early solar system?
Yeah. So this is not necessarily a surprising find because people who model protoplanetary disks, which are the disks that these planets were forming out of, have always included magnetic fields. Because the problem we have is getting these things to form quickly enough. You got to stir everything up. You got to get stuff interacting. And as we see somewhere like the rings of Saturn, things can be in a disk and not interact for a long time. And magnetic fields are one good way of making this interaction happen. And so we've always kind of appealed to them as a way to get things going. And this is basically just confirmation that, yes, there was magnetic activity going on in the protoplanetary disk 4.5 billion years ago. We're not crazy.
Good. Whew. All right. On that note, let's move on. So, Ramin, we've got a strange alignment of quasars. This is pretty weird.
Yeah. So there was this study by let's see, Damien Houtzemakers, I'm not sure if I'm pronouncing it right, and co-authors in Europe, they found that it looks like the rotation axes of quasars are aligned with the large-scale structure of the universe. So what large-scale structure is, so this is related to the dark matter that Brian was talking about before, where in parts of the universe where you have where it's a little bit more dense than average, then dark matter particles come together and form these clumps that we call halos. And then there's also slightly less dense areas which are sort of like filaments, like strings. They're not. It's not like string theory, but they're filamentary structures, and they sort of connect to these clumps of dark matter. And then, of course, in the underdense regions, because if you have dense regions, you have to have underdense ones. Those are sort of you can have what people call voids. Now, so you end up with this sort of like this like web-like structure. Some people call it the cosmic web. And if you look at dark matter in simulations, or if you look at the galaxies or quasars that we observe, yeah, that there's a good image of a large-scale structure there. You can find this structure. Now, in I guess the traditional interpretation of the dark matter halo model, all of you can explain the main properties of galaxies and quasars just from the dark matter halo that it's in. Like how massive, how big is this halo? In the biggest dark matter halos, you have things like galaxy clusters, and you'll have a bunch of quasars. In smaller halos, you have fewer of them. So the thought was that there shouldn't be a correlation beyond the halo. However, some people think, well, maybe you could have an effect such that if an object like a galaxy or a quasar falls in from a filament into a halo, then it could be related to other objects that formed in that filament as well. In that case, you'd have sort of a connection or a relation between things that are in separate halos. And so this is sort of what they're finding here. I mean, some people have detected things like this before, but it's actually difficult to detect. It involves. It depends on what kind of statistical tools you use. I think this is a field that's sort of it's an issue that's ongoing, that's continuing to be studied. So I think exactly how much, if at all, there is a correlation with large-scale structure beyond a halo, beyond scales of what we call like a few megaparsecs, the size of the biggest halos. That's still open for debate. But it's an interesting result, and it could be correct. It could be confirmed. Mm-hmm. They refer to it as spooky alignment. That's sort of a reference to spooky action at a distance in quantum mechanics, and it's because in quantum mechanics you think that particles that are far away, they can't interact faster than the speed of light, but they can nonetheless be related. This is sort of a similar thing, where you can have objects in different dark matter halos that are really far away. They actually could be, these quasars could be related just because they formed in the same filament, and they could be aligned. They could have an alignment signal because of that.
And so if you look at that picture, I mean, I posted that picture, and I'll put it up again. Like if you look at it, you see. Oh, it doesn't want to bring the picture back. I have broken it. Never mind. Anyway, so you saw that I will work with my hand. So you've got the lines, and you've got the quasars embedded within those filaments, really quite lined up, almost like magnetic field lines. Mm-hmm. That it's sort of that same alignment along those filaments that they line up in that way.
It almost looks like there could be some possible predictive power with that too. If you see the orientation of the quasars, then are there filaments there or not?
Right. Yeah, I think it's difficult to. I mean, observationally, it's hard to find filaments. You see them, they're obvious in simulations, and then people try to model, quasars and galaxies and with starting with these simulations, but quasars and galaxies are more complicated than dark matter, and so there's more than one way to do that. So I think that's part of the reason why. There's definitely more to be done on this issue.
All right, so let's move on. So much to talk about. Okay, so David, the Russians launched a very strange satellite, and it did something weird.
This is a news story I've kind of had half an eye on because it kind of falls in my purview of observation tracking. The Russians launched a satellite atop a BrizKM rocket on May 23rd of this year, and what they're tracking right now is this released 6 payloads, and the number 6 payload seems to be doing some very curious maneuvering, and this has kind of made its way around to the general news like NBC and CNN, and I've seen some talk about exactly what the satellite's doing. Now, what most of the major news organizations are leaving out is that amateur satellite trackers are actually some of the ones that have kind of broke this to follow like the CSAT community and a lot of the sat trackers that are out there. These are people that whenever these kind of government or classified payloads are going up, they're trying to spot them and kind of get a rough orbit and see what they're exactly doing. And there's some discussion out there that this might either be some type of advanced technology they're testing for satellite catching or repairing, or maybe there's a more nefarious anti-satellite capability with what the Russians are doing up there. Now, we've tested that. The Chinese did an anti-satellite missile test back in 2008 that showered low Earth orbit with more debris, as if the collision in 2009 later on between 2 satellites wasn't enough. So it's interesting to note that I think there's an amateur connection there as well of what they're actually tracking and seeing and what they're doing up there. So the Russians aren't really talking about it. Roscosmos isn't really revealing exactly what they're doing up there with this satellite, why it's maneuvering the way it is. But it's anybody's guess. You know, you can step up to the mic and give your opinion right now as far as what the satellite might be doing. So I haven't seen it myself. I've wanted to actually piece together an article on this and try to go out and observe it whenever I'm at a dark sky site and get a look at it myself. And incidentally, it is Cosmos 2499 is the name of the satellite.
And I've heard a bunch of speculation, right? Like we've heard that it's, as you said, it's a satellite killer. Is it a satellite repairer? Is it a way to clean up your space junk afterwards and bring it safely back, safely back to Earth to deorbit through into the Earth's atmosphere above a large body of ocean? Is it something that'll observe other satellites up close? I mean, you can imagine
that's probably another good line of speculation that maybe something to observe spy satellites. Incidentally, the X-37B that just landed, there was that same type of speculation around that as well as what it was doing up there.
I don't really buy that personally, because I see these, and you're like, what do I know, right? But the point is, like, amateurs can track these satellites with tremendous accuracy, and they know where they all are. And so NORAD would absolutely watch a Russian satellite approaching, and it's and just hang out right beside it. And I don't think they'd be pleased if that happened. And I think
satellite killer makes better press, makes better copy, but they're probably testing some type of maneuvering technology. Incidentally, with the X-37, a lot of people in the community noted that once we started the military campaign against ISIS over in Iraq, the X-37 altered its orbit slightly. So I think they're testing some type of spy satellite technology. It changed its latitude that it was passing over, so it was making multiple passes over that region that day. Again, that's just me speculating here from a hotel.
Yeah. I mean, do reconnaissance satellites have that much capability? They always talk about retasking satellites, but do they have that much capability to shift?
To a small extent. Yeah, there's orbital mechanics still rules. There's like, if you remember from Gravity, you can't go from ISS over to Tiangong the way she did in the movie. There's a little bit of suspension of disbelief with that kind of thing in a movie. They're radically different. Matter of fact, they went from Hubble to the ISS to Tiangong, which are all in radically different orbits. That was kind of a big boost in the movie. But
well, at least they didn't travel through a wormhole to the
I haven't seen that yet.
A black hole. So no, the science, that part of the science apparently is Kip Thorne worked on it. It's airtight. So anyway, so that's it. I mean, but I love the speculation. I love to watch the speculation, and that's all. That just doesn't pass the sniff test for me. That that any space agency wouldn't watch dumbfounded as another space agency moved a spacecraft right next to some, you know, high-profile reconnaissance satellite, and they would just get on the phone and like back your satellite up.
What I think a great backstory I think a great backstory here is there's people in their backyard that are tracking these sorts of things, and people don't realize you can go out and see not just the ISS, but you can see a lot of. If you see satellites that are in a highly inclined north-south orbit, they probably are spy satellite or spy satellite-related hardware like boosters. There's a lot of them out there, so you can see it from your backyard.
Oh yeah, amateur astronomers know when, not only where the Iridium satellites are, but when they're going to tumble and flash and brighten up. And you can like set your watch by it and walk outside, look up, and then see a flash from an Iridium satellite. So yeah, none of this would go unseen. So that's my opinion. My pointless speculation. All right, let's move on. So Morgan, we've got a new map from of Europa released from NASA.
Yeah, so there's no new information in this map because the last time we got a good look at Europa was with the Galileo spacecraft, which was orbiting Jupiter between 1995 and 2001. And when the mission ended in 2001, NASA built a mosaic of Galileo images of the moon Europa. And you've seen, if you've ever seen a picture of Europa, this is the one that you've seen. And you can see the big cracks and scars and the brown streaks on the surface. But when they built that mosaic back in 2001, they did so with colors that were pretty exaggerated. And that's useful for scientists because you get a sense of what the various components of the image are. But it's less true to what you would see if you stuck your head out of a spacecraft in Jupiter orbit. So now they've gone back and remade...
Death.
Yeah, death first, false colors second. And now they've gone back and remade this image in true-ish color. And so this is much more like what you would see if you looked out the window today. And so what we're looking at here is a hemisphere of the moon Europa, and you can see the white of the ice that covers that moon. But more interestingly, you can see the brown streaks across the surface. And many planetary scientists affectionately call this the brown gunk. And we don't know what this brown gunk is. And it's one of the big questions about Europa. Did this brown gunk come up from the oceans? Is it sprinkling down maybe from volcanoes on Io? We don't know, and this is one of the questions that we want to answer about Europa to better understand the prospects that Europa might have as a place that would be friendly to life. And this month...
Someone should send a mission.
Yeah, and this month we got some pretty good news about a possible Europa mission. The Europa Clipper is a mission that's been in the works now for a number of years to basically go and make a bunch of flybys past Europa, closer than Galileo was able to do, and make very detailed measurements of the surface and use radar to study the subsurface of the moon. The problem is that this is a very expensive mission. Cost estimates have ranged anywhere from like $1.5 billion to $4.5 billion. And this is something that Congress is going to have to move on basically at the appropriations level in order to fund that. And that's always kind of been a questionable action. But this week, the Republicans basically announced who is going to be the next committee chairs of all of the committees coming into the next Congress, which will take office in January. And they announced that the chair of the committee, or the subcommittee that writes basically the science budget for the House from the United States, is John Culberson. And he's a Republican from Texas. And he has been, for years now, one of the biggest supporters of a mission to Europa. This is beyond being maybe good for his district from the sense of having manufacturing and science being done there. This is sort of his personal passion in science, is going to and understanding Europa. And so with him basically now guiding the process for writing the House's science budget, there's a good chance that he will include funding to at least move the process along for the Europa Clipper in the next fiscal year.
And so, what kind of a mission would the Europa Clipper be? What activities would it partake?
Yeah, so it would, as currently designed, it would fly by Europa 14 times over the course of a couple of years. And in those 14 times, it would use cameras to take high-resolution pictures of the surface, much higher than what we have today from 20-year-old Galileo. It would use spectrometers to study the spectrum of the surface to see what chemicals make up the surface, as well as to search for geysers coming off of the surface, like we see at Enceladus, for example, and around Saturn. And it would use what's called an ice-penetrating radar to blast radio waves down through the surface of Europa and try to find that ocean that we think is probably 5 to 10 kilometers below the surface. And if that's the case, then we can better understand the interior structure of the moon.
It needs a lander too.
I was going to say, it needs a Europa lander.
Well, the biggest hindrance for a lander right now are those Galileo images, because the resolution we have now is not good enough to find a safe landing spot. At best, we're talking about resolutions that are generally on the order of like 100 meters per pixel. So you could have like sports stadium-sized boulders on the surface of Europa, and we wouldn't be able to see them. There's no way to pick. Yeah, there's no way to pick a landing site without better information, and that's what the Clipper is supposed to get.
And as we saw with Rosetta, if you can't be guaranteed or you can't minimize the risk of your landing site, you could run into some problems. And in this case, Philae only lasted for a couple of days and not ongoing, with because its solar panels were blocked out.
Right, absolutely.
Or Europa penetrator would be kind of cool, like Deep Impact.
Yeah, that would be great.
Send up a big spray and just analyze that.
Yeah. Punch through the surface.
Yeah, well, we did do that at the moon.
Yeah.
With the L-Cross mission, did that exact idea at the moon. And so it's a workable idea. It's just, you spend 5 years getting, that's the trick.
Well, what about we do one then the other? What if we send an impactor, it splats onto Europa, creates a sort of area that liquefies and then freezes like at a skating rink, and then your lander comes one orbit later and uses that area as its landing site.
If you write that proposal, I will sign on.
Right on. Nobel Prize, please.
And an Arctic sea to melt through the ice.
I don't know. I've seen a lot of science fiction. Landing on Europa is a bad idea.
Yeah, it's a bad idea. There's like worms or something there. All right, let's move on. Okay, so now, Brian, I don't know if you read. Did you look at that other dark matter article? I know you hadn't prepped on this one, but I.
Just a little bit. The basic idea of this one is it kind of comes down to the idea that we've got a lot of evidence to support dark matter, and we keep looking for dark matter particles, and we don't find them. And in fact, we've gotten enough data that we've eliminated some of the models. And this is on the edge of getting problematic, because we have kind of two sets of evidence that start contradicting each other. So this new idea is that maybe we're not detecting the dark matter because it's attenuating in the Earth. So the basic idea is when we have dark matter detectors, these things are buried. They're typically in old mines. And the reason they are for that is because we want to protect them from things like cosmic rays, because these dark matter detectors are really sensitive and they're looking for interactions with nuclei. But cosmic rays can come in, they can smack the nuclei and give a very similar signal. And certainly if you try to do this on the surface of the Earth, you'd get far too many of these stray signals. So they bury them. And the argument here is that maybe they're too deep, that if the dark matter is attenuating as it comes into the Earth, we wouldn't see the signal because too much of the Earth above it is blocking the signal, thus explaining why we don't see it.
Right, and I guess that technique, though, works so well for the neutrino detectors.
Yes.
And in fact, the dark matter detectors are in many cases neutrino detectors refurbished, right?
Yes, they are. That's exactly it.
Yeah, and so it makes sense to think that, these things don't interact, so we should be able to find them in the same way and,
Right.
shield from the cosmic rays. So anyway, lots of stuff on the dark matter front. That's all we're saying this week. Okay, we got one last story from our regular ones. This comes from Ramin, and this is new information about the formation of the Milky Way.
Yeah, so this is it's sort of a summary of some work that a bunch of people have been doing to try to figure out how our Milky Way galaxy has formed. This is a field that's become, I would say, increasingly popular among observers over the past decade. And so what the idea is that you have, so we have a lot of what are called satellite galaxies. So there are these smaller galaxies that are surrounding the Milky Way, and there's sort of a census of them. We think we found, at least from the regions that we can see, we think we found most of them. A lot of them are so-called dwarf galaxies, so they're really, as you can guess, really small, and some of them are barely distinguishable from, say, star clusters or globular clusters. But the thought is that a lot of dwarf galaxies, they get stripped or disrupted somehow, and then they're gone. And so the dwarf galaxies that we see around the Milky Way now might not actually be all of the ones that have been there. And so we have there's something that people call galactic archaeology, and they try to study the ages and metallicities of stars in the Milky Way, and some of them look like they've come, that they have different properties than the average properties of the other stars, and so it's thought that some of those may be due to disrupted galaxies. And then also there are also research that so this is Catherine Johnston and others are working on. They've also found that stellar streams like the Sagittarius stream may be due to a disrupted galaxy, and so it hasn't totally become disrupted, but there's still some structure there. So there's something that people call the stellar halo. It's a confusing term because it's not the same as a dark matter halo. The dark matter extends to much larger scales and is less dense. The stellar halo are basically stars that have been stripped and are just hanging out, but they're not part of the Milky Way's disk or spiral arms. And so this is pretty neat. People are learning about maybe how many dwarf galaxies have come and what happens to them once they fall in. Another example, you may have heard of the Magellanic Clouds, which are actually not clouds but galaxies. They're more massive satellites that the Milky Way has. They're very rare in that it seems to be rare that two galaxies fall into a system at the same time. So they're basically interacting with each other as they fall in. And it looks like the small Magellanic Cloud is being sort of stripped, and it has this really unique tail. And so this is another example of how you can form these streams. And so yeah, people are doing this galactic archaeology and trying to learn about how the structure of our galaxy came to be the way it is.
Well, I know that astronomers can look in the sort of the streams of stars in the Milky Way and identify old gobbled up galaxies as they're still being digested by the Milky Way. And I guess the question is, like, how many of these small galaxies can we digest before we start to turn into more of an elliptical galaxy, or is it going to take a really big impact with another big spiral galaxy to get that final elliptical structure?
Well, so for the elliptical structure, basically what people think is that to form an elliptical, you need to run out of gas. So a spiral galaxy, and maybe not dwarf galaxies, but spiral galaxies do have gas, a large quantity of it, and so you can form. So even if another spiral galaxy, hit the Milky Way, which would hurt, you would have enough gas to form a new disk. So it's basically bigger, older galaxies where they're just running out of juice to keep forming stars. Then if a galaxy hits it and it can't form a new disk, then it stays in that sort of elliptical form. And so some people think, maybe the bulge of our Milky Way is sort of like a small elliptical, but there's some debate in the field about that.
Oh, that's really interesting. Okay, so this is the point where we switch over and we talk about some of the stories that the good folks at the Weekly Space Hangout Crew, which is a Google Plus community. You can search for WSH Crew, and I highly recommend. Some of our sort of diehard fans are there, and they sort of cover all kinds of stories over the course of the week, and then we take a few of them. And we don't have a lot of time for this show because we had so many of the other stories, but I think the big one that we should at least talk about is that Sev Dust Bunny posted, and Morgan, I hope you've been following this, that Philae detected organic molecules on the surface before it went to sleep.
Yeah, I mean, this is sort of just coming out that, Philae completed 100% of its nominal science objectives, and that included basically sampling the surface, performing chemistry on that, and then returning that data to Rosetta, which then returned it to the Earth. And it's not surprising that it found organic molecules on the comet. It's really neat that it did, but it doesn't surprise us because we've long thought that organics are probably common on comets, and some people have even suggested that this is a way in which many sort of life-bearing organic or life-producing organic compounds could have been delivered to the Earth. Now, that's certainly a contentious claim among planetary scientists, but there are people out there who say, if life didn't come from comets, the stuff that made life came from comets to the Earth.
I know there was some talk about the comet.
Sorry, I
we missed
you,
that,
Dave.
David. Can you say that again?
I know there was some discussion about, I don't know if they found anything out about as far as their chirality, like their left and right-handedness of the organic molecules, if they were similar or different than what's on Earth, but I haven't seen any, if they found anything like that.
I haven't seen anything about that yet.
But I think that was the same instrument, right? That maybe they're still analyzing the data or something. The COSEC, is that what it is? I think that's what it's called. But yeah, they first detect the organics and then try to find the chirality.
So I mean, the chirality. So if people don't understand what that means, the chirality is the
direction.
I think
the
the
left,
left
right.
is a good example of, like, they're the same shape, but they don't occupy the same space. They're flipped in 180 degrees.
Mm-hmm. And so if they were the other way, then that could mean theoretically you could have life that has, later on you could have life that could form with the basic building blocks, but the building blocks all go in the opposite way.
Yeah.
Be amazing. And that actually, I think if I understand again correctly, that if they actually do find any kind of organic molecules or even some fragments of life on Mars and other places like that, that's one of the first things you're going to be looking for, because then the question is, does the life have a common ancestor? Is it the panspermia idea where you've got bacterial life traveling from Earth to Mars or Mars to Earth, and that they're all just connected? Or did life arise completely separately in locations?
If their chirality is different than ours, it'd be fortunate for us because they couldn't eat us, and vice versa, because they would be able to digest our proteins.
There's always a silver lining.
Yeah. Take that, killer Martian. Can't eat us. Cool. Why don't we wrap this up then? So, and I apologize to the folks at the WSH Crew. That one came from Sev Dust Bunny, but I actually, I'm sure a lot of you were talking about it this week. There's a bunch of other stories, but we had a ton of stories this week. So, but I just want to remind everybody, if you want to join a great tight-knit community, if you enjoy the Weekly Space Hangout, plus join the WSH Crew. Okay, so let's give people a chance to shamelessly self-promote. Brian Koberlein, where do we find out more?
You can find me on Google+. You can find me on Twitter at Brian Koberlein. You can find me on my website at briankoberlein.com, where I blog every day. You can support me on Patreon. That's basically where you can find me.
I will let that one slide. All right.
Patreon,
yeah, but patreon.com/Brian Koberlein.
Brian Koberlein, yep.
And I know you hit a new milestone, and really everybody should jump on board and help you hit the next milestone. What's your next milestone that you want to hit?
Video.
Yeah, at what level?
You sound thrilled about that.
500.
$500. See, for all we have to do, and I am one of Brian's bosses.
That's true.
On Patreon.
And so is Ramin Skibba.
Yeah. Yep. So all of you watching, you know, if you want to have Brian make more space videos, you just need to go to his patreon.com/Brian Koberlein and just kick in a couple of bucks a month and contribute to the work that he's doing, and really force his hand to make us some space videos. So and he's had lots of practice because another couple of Brian's scripted episodes of our videos came out this week. So we talked about how long it takes for a black hole to form, and another one, and I forget what it was. But you can check that out on our YouTube channel on Universe Today. In fact, the one you're watching right now. Okay, Dave Dickinson, where do we find out more?
Yes, I am at Asteroid with the Z on Twitter. I write about observational, all things going on in the sky for Universe Today at least once or twice a week, and I'm writing about me and my wife's adventures and our dog across the U.S. on Astroguys and on Canada.com. And I am also putting together my one blog post that takes me 6 months to write. I'm writing about everything that's going on in the sky for 2015. By the end of December, I will have that on Universe Today. So if I'm not on another Hangout by then, look for that. I hope to be on there to talk about it by then. But like I said, it's the one blog post that takes me 6 months to write every year.
Yeah, prepare yourselves for this, because it's a monster. And didn't Kevin's going to try and make some simulations?
We were talking about doing simulations, and I'm like, that's great, because graphics takes about half the time just to do a lot of those. So if I can outsource those, that's awesome. So.
Yeah, I'm talking about Kevin Gill, who you can track. All the animations, all the custom animations that we have in our videos, and he's just terrific. You can check out his work on Google Plus and his apoapsis.net. Anyway, apoapsis is his website, and he's got all the simulations. Yeah, just amazing stuff. So check it out. I should get him in the Space Hangout sometime. Okay, Morgan Rehnberg, where do we find out more?
Yeah, well, we didn't get any questions time today, so you can find me over at the Google Plus Space community talking about all of those for the next couple of hours. You can follow me on Twitter at Morgan Rehnberg, and you can find my website at cosmicchatter.org.
Awesome. So just a reminder, go to the Google Plus Space community, not the WSH Crew, and Morgan will answer whatever questions you have about space and astronomy. Like, when are you going to have a Patreon campaign? Things like that.
I don't want responsibilities.
Very true. You have some responsibilities. Actually, and you just started writing for us at Universe Today.
I did. I posted my first article this week.
And what's the title?
Alone and Confused, Philae Breaks Our Hearts.
Oh, I saw that.
That was fantastic. It was just great, Maria. It was really great to have you join the team. Ramin, where do we find out more?
You can find me on Twitter at Ramin Skibba, and you can find me at raminskibba.net, where I blog about astrophysics news as well as science policy issues. And then you can read about my work, my research at UC San Diego, where I work on galaxies, large-scale structure, and dark matter.
Fantastic. Okay, great. And of course, I'm Fraser Cain, F Cain on Twitter, Fraser Cain on Google Plus. You can join my YouTube channel. You can read my website, which I publish, Universe Today, and lots of other things. And you should listen to this weekly space show that we do called the Weekly Space Hangout.
It's pretty good.
All right. Thanks, guys, for joining us this week. Thanks, everyone, for watching, and we will see you all next week.
Bye. 2 weeks.